Welcome, friends. My name is Cherie Kagan. I'm the Stephen J. Angelo Professor in Electrical and Systems Engineering and Associate Dean for Research at the University of Pennsylvania's School of Engineering and Applied Science. I'm your host for Penn Engineering's Innovation and Impact podcast. Our podcast shares insight from some of the leading experts from around the world who are Penn and Penn Engineering faculty and researchers who are bringing to you the latest breakthroughs and innovations in science, technology, and medicine. Today's podcast is about energy and sustainability. So to start off, protecting the world we live in and leaving it a better place for the future is something that is a global concern for everyone. From the unique perspectives each of you brings, what do you see as the overarching vision for achieving sustainable energy in the near and distant future?
I'm excited about increased investment in relatively mature technologies like wind and solar. I think rolling out transmission lines, utility scale batteries, all of that is happening in practice. And I think there are a lot of emerging technologies coming down the pipeline that are even more exciting. So I think in the near term, it's really about executing what we know how we can do. And then in the medium term, I think there are probably going to be some harder decisions that need to be made. In my particular field of data center computing, the industry will have to figure out when it wants to compute and by how much. And it will also have to figure out whether it will want to invest in some of these other more speculative emerging technologies as well. So I think the near term is pretty clear. I think the medium term is going to be very interesting, and the long term is going to be very hard.
So I wanted to ask, the world's population is expected to increase by nearly 2 billion people in the next 30 years, from the current 8 billion to 9.7 billion by 2050, and could peak at nearly 10.4 billion in the mid-2080s. How do you see the balance between energy supply and demand evolving in the coming years, especially with the growing global population? So maybe I'll kick it off to the energy supply side first, and then ask the demand side.
So, fortunately, there is some good news in that energy supply picture, as well as in demand. But in particular, with trends, the amount of economic activity that is being extracted from each unit of energy is increasing. So efficiency in many metrics is helping to counteract some of the growth in population. But the greatest challenge is that many of the people that will be living through the next century, they are still evolving in terms of their total level of technology access. And it's an equity issue in terms of how much energy and quality of life opportunities can be impacted by energy. So I think one of the things there is that a focus on efficiency, but in particular also helping some of the emerging areas with large demographic changes to make that transition as effectively as possible. So the adoption of technologies that help us to leapfrog and avoid some of the pitfalls of earlier deployments of technology, I think that's the imperative. It's really an issue of having solutions that, as Ben had mentioned, it's about execution in the short term, but we have to help other areas around the globe to make good choices that are beneficial for them, but also help the planet. So I think getting that impact factor per additional person down is one of the greatest challenges in this next century.
I absolutely agree with that point. I think the equity issue is top of mind. I think when we talk about developed economies, we're talking about AI and computing, and that's a very different question than the one that you would be asking in a developing economy, where they're fairly far away from the standards of living that we might be accustomed to here in the United States. So I think it is also interesting to note that the most advanced technologies are being deployed in developed economies where population growth is slowing. Whereas where we see the most rapid population growth are areas where they still have quite a ways to catch up in terms of electrification and the standard of living question. So I think there are two different questions, and they should probably be thought about separately.
I think you guys made great points, Chris and Ben. And I think, given my own kind of personal experience in industry, now like in academia, so in the field of power electronics development, I think both are in the community and the industry. People care a lot about cost, when we're trying to develop like solar inverters or motor drive for electric cars, cost is a great consideration, in fact, for these technology innovations. So, like Ben said, if we can cut down the cost of these renewable technologies, and maybe we can actually help to meet the demand when we have a much greater population.
So I'd like to maybe delve a little bit further into these questions about technology, and in particular, I'll sort of split them up on the supply side and the demand side. So maybe I'll start off with a question that I'll start with pointing to Chris. Energy supply can come from different technologies. They could be solar, nuclear, catalysis, wind. I won't hold you to choosing just one area, but what materials and devices and in what technology spaces do you feel are most important or are poised to address the need for an increased energy demand? And, well, beyond just greater funding, what advances in science and engineering are important to make this happen and to ensure that these technologies are sustainable?
It's a great question. So there are opportunities for all of those different energy pieces of the puzzle to come together, and I think we do need all of them. I think some of the most exciting developments in terms of large-scale deployment we see in the area of solar, coupled with thoughtful ways of long-term energy storage, not just electrical energy storage, but using hydroelectric, pumped hydro as a large-scale grid backup for power. So integrated systems are necessary for success. But the really exciting news is the tremendous decrease in the cost per unit of function for solar-related systems and materials. And so that opens up new opportunities for electrification that I think we'll hear more about in terms of transitioning away from other types of energy carriers that we work on now. And so I think in the portfolio, there are advances that are coming from new understandings of light matter interactions that come from different fields, from areas that involve photonics and engineering of different semiconductor systems, as well as understanding more about just the opportunities to continue to improve the cost to benefit sort of balance and getting more for each of those components. But I think it has to come together. The generation of materials is only economically optimized when we have appropriate levels of storage that allow us to balance out the demand.
Great. Well, with that prompt there, maybe I'll ask Lei if you could come in with the energy available that might come from different technologies. Could you say a little bit about conversion, of how you'd use that energy?
Absolutely. I find it very interesting that, Chris, as a material science engineer, you mentioned the integrated energy storage system first. While as a systems engineer on the side, I'm particularly excited about the advances in material science. For example, over the past decade also, the wide bandgap power semiconductor devices have really been showing great promises of, like, they can perform much better than the legacy silicon power devices. What that means is, like, they can build energy conversion systems, essentially power electronics, for all kinds of applications, no matter solar energy generation, wind energy generations, or HVDC systems, or even better, just the electric cars. These wide bandgap materials can make the energy conversion system from battery to the motor, all these kind of thing, much more efficiently. But also there are a lot of variability of applications. So it requires a lot of customized design optimizations from the engineer side to fully utilize the potential of these devices. So that's a lot of there's a lot of efforts going on right now in the areas I'm familiar with right now.
Maybe I'll point the next question to Ben to start with. We've been hearing so much about AI over the past year and its growing thirst for energy. By 2040, some experts think computing and communications will gobble up most of the world's energy. With AI's rapid speed of innovation and increasing popularity into the mainstream, how do we ensure its energy demands are sustainable?
That's a great question. And I think this goes to the earlier point about exponential growth in demand for computing driven by artificial intelligence and machine learning. And when I think about the carbon footprint associated with AI, there are really two parts to it. The first is the embodied carbon, that is the carbon going into building the chips, building the data centers, and so on. And we need to care about the size and scale of our systems. And then the second is the operational carbon, the amount of electricity we're consuming as we compute. And I think both are going to be incredibly important. Understanding how we deploy hardware, how we lengthen their lifetimes, how we decouple the provision of different hardware components like microprocessors and memory systems so we can upgrade them independently. All those things will reduce how much we manufacture from our semiconductor fabs, and that will help us on the embodied carbon side. On the operational carbon side, I think it's all about electricity usage and data centers. And when we think about electricity usage, there are three parts there. The first is data pre-processing. How do you collect and organize your data? The second is training. You've got a large model. How do you learn it to perform the tasks that you wish to perform accurately? How do you teach it? And then the third is inference. Once you've got a trained model, how do you use it and respond to human queries? And I think historically there's been a lot of concern about the training side of the question, and I think certainly those numbers are big. But what I'm more concerned about is actually on the inference side. If everyone and their mother and even their grandmother might be using AI for various capabilities, then the data center computing in the background is going to be working that much harder. So I'm worried about a scenario where a lot of the AI is being invoked transparently. You don't even know what's happening, but it's being done for you in the background. Or people start using AI like they are currently using search engines. Those sorts of scenarios will lead to a dramatic increase in the carbon footprint. So I think those are the concerns about sustainability. There are lots of solutions that we're thinking about, but I think that's sort of the concern that people are raising in the popular press when they're saying computing might consume an increasingly large share of global energy.
It might speak to needing more power. Lei, did you want to add anything?
Yeah, Ben gave a great overview of how the actual power is like allocated inside the chips or the computing systems when you're trying to do machine learning or AI training. I think add to that, power is not transferred and distributed efficiently. To sustain like reliable operations of a data center, you actually need a lot of more power rather than just the actual power you needed to do the AI training. You would need power for cooling. You would need power for equipment to support all these servers and then memory systems. You also need power for the facility. So when you take in all these power into considerations, it's a factor of like much more than the actual power you applied to do the AI training. So when we talk about sustainability and AI, I think essentially if we want to build more efficient data centers to continue develop advanced AI, we have to take all these considerations in mind. We need better cooling technology to reduce the cooling power. We need better power conversion technology so that the actual power delivered to the point of load is kind of like matching what the grid can provide. So I think, I just want to add that like there's a lot of more power going on and needed for running a data center other than just to do the advanced AI training.
Yeah, it really looks like points to the co-design of both the data side, the sort of software side, as well as the hardware that's needed to deliver on these kinds of systems.
Maybe if I could add, one of the points of optimism is because it's so hard to optimize the performance in these complicated systems, actually the application of AI as a way of helping people to overcome the challenge of addressing efficiency in many different processes. I think that might be one of the bright spots in figuring out how to do this the best way, is to use the tools that are evolving for multivariable co-optimization.
When we think about AI and other emerging tech, are our only options to decide if the benefits of the technologies outweigh the negative impact on the environment? Or could there be ways to make AI and other emerging tech more sustainable? Should we push engineers to innovate with sustainability as a priority? Ben, do you want to take this one first?
Sure, absolutely. I think that's absolutely right. Engineers do need to innovate with sustainability in mind, and I think for a while it's been we've seen in industry two separate teams, one developing the core technology and one focus on sustainability and publishing the annual sustainability reports. And I think there has been for a while a disconnect between innovation and sustainability. But I think I'm optimistic that that's changing. I see increasingly a large number of engineers and technical teams thinking about sustainability and eager to engage with the sustainability teams. And I think that will go a long way in terms of closing this gap and innovating with sustainability. I think there are a couple of directions where this closer collaboration could play out. I think the first would be when you think about energy supply and the time-varying supply of carbon-free energy, are there ways that you can manage your data centers, schedule your jobs, incentivize users to consume less energy? Data center operators are increasingly thinking about questions like that. Secondly, I think there are a lot of computer architects or system engineers thinking about the precise mix of hardware in the system. How do you allocate processors, memories, network bandwidth, and so on in ways that really reflect the performance that is needed, but also reduce the amount of wasted resources that are being allocated. And I think collectively, these directions will help us better align what is coming off of the grid, as Lei was saying, with what users demand within the data center.
Maybe I'll say come back just even on a hardware side is think about, if we really have that much energy consumption in data centers, whether, Chris or Lei might want to comment on the opportunities to sort of harvest that waste energy.
So I guess maybe I would start just with the idea of cogeneration has been prominent in many other energy technology areas. When one thinks about the density of energy created by data centers, then the possibility of using that waste heat for either chemical processes, for water purification, for other things that are inherently energy intensive with respect to thermal energy might be a nice pairing for sure. And I think one of the parts to consider, as you said, about scheduling and understanding more about how to optimize the timing of calculations, Ben. I also sort of wonder about whether the physical location, so what geography or even efforts to sink some data centers into the ocean as a way of cooling. Some very innovative things are being thought about for the thermal management side. And so I guess with the cost of the energy and the design to efficiently manage that energy increasing, I guess we have incentives to do better on out-of-the-box solutions.
Absolutely. And I'll say on data center placement and geography, it also goes to Lei's question about the grid and where we hook up. Surprisingly, it turns out that there is a cluster of massive data centers in Northern Virginia, and they are beginning to overload the grid. And they're saying that Northern Virginia is unlikely to meet its renewable energy targets given the number of data centers being built and drawing energy from that grid. So site selection and placement, whether it be underwater or in just cooler climates or places where there's more renewable energy, turns out Nebraska and the Pacific Northwest are fairly good places. It's super important to think about because we've really got to connect and think about this holistically, as you're saying, Chris. Absolutely.
And I think some of the companies are already doing that. I think, if I'm correct, Amazon and Google are committed to, by the year of 2030, to source and match this zero carbon electricity demand and supply on a 24/7 basis within where the power plant is located areas. So people are aware of that and doing that.
Looking ahead, what breakthroughs or advancements give you optimism for a more sustainable energy future? How can educational institutions like Penn continue advancing energy sustainability, and what initiatives on campus and in our labs succeed in this regard?
I guess one of the parts I would start is that the greatest thing is awareness. So having the opportunity to develop a group of students and a community that are sensitive to these issues, but even more importantly, that we reach across disciplinary divides so that we have scientifically literate people that are working in all different areas of society. It would be great if people going into public service and so on had exposure to the aspects of the scientific method and understanding what challenges we face. So I guess from the role of the university, there's a role in research, but there's also in education. I think one of the greatest things that we can do to give more momentum to that is emphasizing what we're doing on campus and getting students involved in energy efficiency issues, making choices that have a clear outcome in terms of even how we carry out our work on campus with an eye towards reducing the amount of waste and really making that part of their philosophy in terms of their training.
Lei, do you want to take that question next?
In terms of technology, I kind of like mentioned earlier, it's in the field of power conversion. There would be the wide bandgap power semiconductors. In theory, they can perform like orders of magnitude better than the devices we're currently using. But in practice, due to some materials immaturity and then technologies, they're not really living up to the full potential of these promises yet. So like that would require a lot of research to figure out how do we actually get the true potential. On the things that like in an institution like Penn, what we can do, I think one of the aspect I have in mind is about like workforce development. Even though I say these devices are not living up to their promise, but they still offer practically like 2 to 3 times or even 4 to 5 times better performance metrics compared to silicon devices. So a lot of the industry are actually trying to develop better electric cars, better solar panel inverters, or better battery storage energy systems using these devices. So we need a lot of engineers who can actually build things using these devices. So I think developing curriculums and then courses that can help educate young generations of engineers to learn about these promises, but also the practical considerations while we're trying to use these devices to, and then hopefully these courses give them enough training, and then they can take these training and then actually help us to develop better renewable technologies in the industry. That's kind of the thing come to my mind right now. Yeah.
Great. Yeah, I am really excited about many of these new technologies that are coming down the pipeline. I think one of the directions that I am very optimistic in is the ability of computer scientists and computer engineers to incrementally improve the energy efficiency of compute. We've seen this with general purpose microprocessors since the 90s, where you have a baseline high performance processor, and then over multiple technology generations, those technologies became increasingly energy efficient, just as people converged on the problem and proposed different solutions here and there. I think we're very close to that for AI and ML. I think we've given artificial intelligence a lot of room to run just to assess the maximum potential and the capability. But then once we've identified that capability, we can go back and think about how we can compute the same answer with far fewer calculations. And that would dramatically improve the energy efficiency on the software side. I think on the hardware side, there are a lot of computer engineers thinking about custom hardware platforms that will help us, again, compute the same answer with less energy. And then in terms of data center design, what I'm super excited about are unconventional sources of carbon mitigation. I think folks in our industry have been talking a little bit about modular nuclear reactors. Others have been talking about direct air capture. These are super expensive solutions today, but we're going to be keeping an eye on those solutions and determining at what point the costs justify the benefits. So I think the solution space, the number of tools we've got in our toolkit is fairly large, and it's just a question of what combination of these tools makes sense. I guess the last point I'll make is that I think there is an interesting intersection between machine learning and game theory at present, where if you're trying to convince people to change the way they consume energy, can you learn how they consume energy? And can you come up with policies that incentivize them to consume less energy in different times of the day? And I think there's a rich community of researchers here at Penn and elsewhere that are thinking about those questions, and we're really excited about engaging with those researchers as well. I guess the last point I'll make about students is that I'm constantly surprised when I talk to students how many of them are passionately interested in sustainability, and they are constantly learning and seeking opportunities to engage with more courses or more faculty or actually lab experience. And I think that's something Penn should definitely go deeper in, engaging our undergraduates, exposing them to the research and the latest in the technology, because I think there's a lot to share.
I think this is also a great example. Penn Engineering has signature initiatives in both energy sustainability and in data science. And I think the examples that you just gave, both educationally and in research, really show where the collaboration of these different efforts really come together. So I wanted to, thank all of you. I wanted just to ask you to sort of reflect for a moment. You're all at different stages of your career and working on different aspects of energy and sustainability. So I wanted to open up to sort of ask you, what do each of you think or see if you think about the future, or might reflect on where you are in your career and the kind of impacts that you look to make in this space of energy and sustainability?
For someone like myself who's had an opportunity to work both in industry and now for extended time in academia, I think the parts that I'm most excited about is that talent development that we spoke about, the passion that we see in students, but that's coupled with many big advances in terms of the tools and techniques and things that we can apply to solve problems. And for something more specific, I think as a materials chemist and in chemistry broadly, I think the electrification of society and the interconversion between chemical energy and electrical energy is one of the biggest areas that I've seen as a transformation point. So I think the next couple of decades of chemistry will be dominated by the interconversion of energy in ways that will be extremely important for sustainability. And I think it's wonderful to be launching students and helping coworkers to really chart their course in that direction.
Yes, I absolutely agree with that. I think students and training is one of the most important things we do here at Penn. I think the other focus I would have is impact through industry and changing the way people think. As I've progressed through my career, I think I've become less passionate about developing a widget X that I hope that a company will adopt, and more about changing the way companies think about a problem, perhaps because my PhD students are doing research in the space, and then they may go and do an internship and work with the teams and try to influence the way they think about problems. And if they adopt the solution we come up with, that'd be amazing. And if not, at least they're thinking about the problem in new and interesting ways. So I think impact through deeper engagement with practitioners, I think, is an increasingly big role in my group.
I couldn't agree more with what Ben said, especially given my own experience. Like I spend more time currently right now, more time in industry on the other side now, like as academia faculty. In the future, definitely we mentioned a lot of discussion about like how can we train workforces or engineers to develop better renewable technologies or this kind of thing. But at the same time, I'm also very passionate about like how can we develop technologies, especially like better power conversion technologies, so that we can enable new applications, not just the applications we have mentioned about, like electric cars, solar energy generation, integrated energy systems, battery energy storage management systems, this kind of thing, or AI. I'm really excited that if we can make a lot of power conversion system much smaller and more efficient, perhaps we can enable new ways of generating things we need. One particular example I can give is this plasma assisted fertilizer generation. So typically RF plasma can be used for like semiconductor fabrication equipment, but like plasma are also like very reactive gases. They can cause reactions if you put nitrogen and water together. So like if you place non-thermal plasma near the interface of nitrogen and water, you can essentially help produce fertilizer that can, without any kind of like carbon emissions. If your electricity used to generate this RF plasma is also from renewable sources, then everything is carbon free. So like, and this development of this new application would require a lot of efficient power conversion systems. So I think there will be more opportunities like that. That's just one particular example. So I guess to circle back, not only we should upgrade our current technologies to make the renewable energy much better, but also we should be creative and then create a new applications using energy efficient solutions.
So I really love this discussion because, I'm a energy supply. So I live on the energy supply side in my own research, but it's been very interesting to listen to all of you speak and almost speak in the need in each other's areas of research that all have to come together in being able to address the challenge that we have in the future of having an energy sustainable future for our planet. And so I wanted to know if as you think about the challenge, perhaps even of thinking about integrated systems, how do we integrate across all of the areas of your research or of research that's adjacent as we think about energy supply and demand? If you wanted to share some thoughts about how do we succeed in developing, whether that be a culture, whether it be the right sort of implements or tools to be able to integrate across these technologies to make what you each spoke about really happen.
One of the parts that Ben touched on earlier is just understanding how people use and approach technology change, right? So use energy, how we can influence that. I think one of the parts that I think about in that cross-training aspect is to help scientists to become more thoughtful about how their contributions will be received by the ultimate customer. So things that translation happens through entrepreneurship and innovation. It also happens through policy and influence on regulatory pieces. So I think having scientists that are more comfortable, open to interacting with those communities, I think is very important. I would say this in the same breath that it'd be wonderful to have more people with those interests ultimately in their careers that can be welcomed and supported in their exploration of some aspects of scientific training, so that we can make it a more effective coupling as we go forward.
There's a lot of learning to do across different disciplines to talk the same language, for sure.
Absolutely. And I think both in electrical and systems engineering, as well as computer and information science, I think these questions cut across the hardware-software boundaries. So we've got to be able to understand what the software needs and how to design the hardware better. But increasingly, we're also thinking about infrastructure, whether it be power delivery and connections to the grid and emerging supply-side technologies that could change the nature of the energy we consume. I think all of that is incredibly important. And just sitting here, I feel like there are a lot of connections that we could have right now and start projects on many of those questions. So I think we're sort of lucky, I think, at Penn to have so many people working in these areas that we can connect with. Absolutely. And I agree with the connecting with the business and economic side of it, and also with the regulatory and legal side of it. All of that is super important.
Yeah, I think Chris and Ben made a great point. Collaboration within the Penn community, all the way ranging from materials to circuits and hardware architectures to software co-design, co-optimizations, collaboration with industry. We should actively reach out to the researchers or companies in this industry for like energy generation, energy supply, or for like AI, different industries, and then actually asking them about like, what kind of problems you're hoping to solving the most, and then initiate the conversations. So yeah, just kind of strengthen the 2 points Chris and Ben has made.
Well, I want to thank you, Chris, Ben, Lei, so much. You've been so generous with your time and insight, and I'm certain our listeners have learned a lot throughout our discussion. So I want to thank our audience for joining us for Penn Engineering's Innovation and Impact podcast on energy and sustainability. I want to invite you to please subscribe to Penn Engineering's Innovation and Impact podcast series on your favorite podcast platform and watch a video of this recording on Penn Engineering's YouTube channel.